Hi everyone, it's time for reactions. Let's see a few reactions that benzene can do. So let's turn to our key concepts. Unit 1, Part 3. You can find these on Canvas. And let's break this down. So there are 8 reactions that are most important for benzene, and they're all substitution reactions. Not too surprising, because as you saw in the previous videos, benzene is incredibly stable. Those 3 carbon-carbon double bonds survive lots of reactions. It's just a very stable setup. And so what popular reactions we have are those that can actually substitute a hydrogen on the benzene ring for another group. And we got 8 of them here. So let's kind of take a look at these. Well, let's break down the name first. Electrophilic, that means the reagent is seeking electrons or something negative. And it turns out all the new groups that are going to be substituting on the ring are the electrophiles. I'll point those out in a minute. So the name of the reaction is called electrophilic aromatic substitution. Pretty straightforward, right? So the reagent's electrophile. You're doing a substitution reaction on the aromatic ring, swapping out a hydrogen for something else. Oh, that's a key point. So once a new group has been presented on the ring, it's unlikely that that group will leave. If you do another substitution reaction, you're going to only substitute hydrogens. Okay, so more on that later in a future video. Let's see, let's just get these reagents out of the way. There are 4 reactions that'll put a halide onto the benzene ring in place or in substitution for a hydrogen. So we need an electrophile that consists of a halide. So the halide needs to seek electrons. The thing that seeks electrons the best, an electrophile that's really good at being electrophilic, is something that's positive. So what's going on in these 4 reactions, actually all the electrophilic aromatic substitution reactions, is that you're creating an electrophile that carries a positive charge. So you're trying to create F+, Cl+, Br+, and I+. And if you're cringing, good for you. You got a good sense for chemistry. The halides like to be negative. They're actually quite stable as negative anions. So what do you think happens when the anions are positively charged? Ooh, they're really cranky, very unstable, and they can attack the very stable benzene ring. So that's the key. We're creating some powerful cations, powerfully reactive cations that have enough oomph to actually overcome the stability of the benzene ring. But benzene wins in the end. Even though benzene gets attacked by these reagents, these electrophiles, at the very end of the mechanism, we'll still have a benzene ring. And the end result will be a hydrogen on the ring. If you look at the screen, we're going to substitute this hydrogen and put on a fluorine. And then I was just consistent. There are 6 hydrogens on benzene. Any one of the 6 can get substituted. But for my drawings, I just put the new group in the upper right corner. So the specific hydrogen that's being replaced or substituted is in the upper right part of the benzene ring. Okay, as you go down the periodic table, anions become more stable, and so do the cations. They're just larger atoms, and there's more room, if you will, to stabilize either the negative charge or the positive charge. So iodide's the easiest cation to create, and bromine and chlorine less so. Fluorine, incredibly difficult. So we got this crazy reagent called F-theta-BF4. And I'll show you the structure in a minute. You can memorize that. You should at least be able to recognize it in case I draw it. So for those of you who are not used to my exams, there will be a question on our future exam where I'll say, hey, choose the correct reagent. And you'll have to, I will either write out F-theta-BF4 or I will draw the structure. And then you'll have to recognize that that's the reagent that puts fluorine on the benzene ring. There'll be a different type of question on the exam where it'll say, please, did I say that right? Where you actually get to write in the reagent. Yes, there's a question where you supply the reagent. Now you get to choose. You don't have to draw the structure FT to BF4. You could just write F-TEDA-BF4, and I give you full credit. Okay, that's the hardest one in the whole list. So we got the worst out done first. Easier ones are Cl2 and FeCl3. And bromine is Br2, FeBr3. Okay, I love these two because look at all these chlorines in the reagents. There's 5 chlorines total. So you probably put a chlorine on the ring. For bromine, there's 5 bromines. So you're probably putting a bromine on the ring. Yay. Okay, so those are nice. And there's some nice set of reagents. You just have to remember that you have to add 2 molecules. One is the elemental form of the halide, chlorine, Cl2, or bromine, Br2. And then we need an iron catalyst bearing the same halides. So FeCl3 and FeBr3. And then why doesn't iodine follow the same pattern? I2, FeI3. Well, the FeI3 is just not very stable. So scientists discovered we need a more stable catalyst, so let's use copper chloride. And because iodide happens to form it's easier to form the cation, the chlorines from the copper don't react. So this one's a little trickier for students. If I say, hey, draw the product of this reaction. And remember, there's no rules that say one reagent always has to be on top of the arrow, and another one always has to be on the bottom. It can be drawn in any way. Now you have a little, you have to recall some chemistry and say, okay, what set of reagents is this? What does it do to benzene? You have to remember it substitutes a hydrogen, and you get to pick. You can pick any one of these 6 hydrogens to substitute with iodide. So there's the product. Okay, that's how you put a chlorine on the ring. There's some other things you can put on the ring instead. You can put on the nitro group. So remember in our previous naming video, we talked about memorizing the nitro group because it's really common. Well, now here's how you can put it on the ring. Use nitric acid, HNO3, mix with sulfuric acid, H2SO4, and that will substitute a hydrogen on the ring with a nitro group. Ooh, so in the lab, be very careful. Nitric and sulfuric acids are very corrosive, and they're strong acids, right? From Gen Chem, you'll hopefully recognize those 2 as the strong acids. Okay, but you mix the 2, and you'll just have to remember that the sulfur part doesn't go on, it's just the N part. And you lose an O. Nitric acid has 3 O's, 3 oxygens, but the nitro group only has 2. I know. So get some practice, and we'll commit that to memory. If both your reagents have sulfur, SO3, sulfur trioxide, and sulfuric acid, both reagents have sulfur, then the sulfur goes to the ring. And the sulfur brings along the SO3 and adds an H. This is actually the sulfonic acid group. And the whole molecule is called benzene sulfonic acid. You don't have to memorize that. You might see in the homework the name. So there you go, just in case you encounter it later. But I'm not going to ask you to name benzene sulfonic acid on the exam or draw it. But you'll have to be able to predict the product, right? So if you see a benzene ring being treated with SO3 and H2SO4, you need to know that, hey, the sulfonic acid group, SO3H, goes to the benzene ring. And the sulfur atom is the one that attaches to the ring. Well, we draw out the full Lewis dot structure. So if you know the structure of sulfuric acid, which looks like this, that's H2SO4, then you know the benzene sulfonic acid group. You just take off an OH group and you put the rest of the structure of sulfuric acid onto the ring, connecting sulfur to the carbon. Okay, those are pretty straightforward. They're useful, but the most useful ones are these so-called Friedel-Crafts reactions. So two scientists, I don't know their first names. One guy was Friedel, the other one was Crafts. They worked together on these series of reagents, and these are actually quite powerful. You can start with benzene and use methyl chloride, and the catalyst is aluminum chloride, and you can put a methyl group on the ring. You can also start with ethyl chloride and aluminum chloride, and you can put a ethyl group on the ring. You can also start with, well, let's shake it up. Let's use I was going to say isopropyl chloride, but you know what? You're not restricted to chlorine. You can use the bromide, the iodide, not the fluoride. Carbon fluorine bonds are actually quite stable. Teflon consists of a molecule that has a lot of carbon fluorine bonds. It's really stable. Anyways, you don't have to use chlorine. You could use bromine or iodide. Stick with aluminum chloride, though. It's a more stable catalyst. Aluminum bromide exists, but everyone uses aluminum chloride. So we're not going to change the catalyst, even if we change the halide on the alkyl halide. And what do you think happens? Do we get a straight chain of 3, or do we get a branching chain of 3? Well, wherever the halide is your point of connection. So the halide's here in the middle. So the middle of 3 carbons needs to connect to the benzene ring. You get isopropyl benzene. Cool. Friedel-Crafts acylation, whoa, didn't mean to mark up the screen, is the same, has the same pattern. The difference, though, is you start not with an alkyl halide, but with an acid chloride or an acyl chloride. This functional group has a couple of names, right? The halides still don't have to match. However, if you have acyl bromides where you change this chlorine to a bromine or an iodide, they're really unstable. So no one does that. We're just going to keep the chlorines the same. So, and then it does not have to be a methyl group here. It can be anything, as long as it doesn't interfere. We'll talk about more about that later. So if you have an acid chloride with another benzene ring here, that works just fine. Keep using aluminum chloride as your catalyst, and this is still a Friedel-Crafts reaction. The benzene ring, and I guess I keep picking on this hydrogen, the hydrogen on the benzene ring gets substituted with the acyl chloride. Wherever the halide is attached is a point of connection for the rest of the molecule to go to the benzene ring. And actually you can make a ketone here. That's cool. And you can decide how you want to construct your ketone. You can make this methyl ketone, methyl with benzene on a ketone, or, oh, whoops, that was a benzene ring. So we still got a benzene ring. So now we have 2 benzene rings on the other side of the ketone. You can do whatever you want. Let's draw it a different way. Let's draw a string of, how many carbons is that? Got 1, 2, 3, 4, 5, 6, and a chlorine. Why? Brain. Aluminum chloride is your catalyst. And now your product is, well, if it's benzene, you get to pick any of these hydrogens. So for convenience, I'm picking this one. There's my 6 carbons. And then right here, I would draw the chlorine. But instead of drawing chlorine, I attach the benzene. There you go. And you got another ketone, string of 5 carbons on this side, and a benzene ring on the other side. Cool. Okay, so you need to find a method that works for you for memorizing these reagents and how they create products. So whether you use flashcards on paper or you use an app, whatever works for you, whether you quiz each other on Zoom, I don't know if anyone does that, FaceTime each other, get some practice in the homework, that'll help. See if you can do some of the homework problems without referring to this list. That'll help you memorize those reagents. Cool. Oh, I guess I already covered this. The last 2 reactions Can use different reagents. You just modify the numbers of carbons here, and you have a choice of modifying the halide. Most students and teachers don't change these halides though. So you can change the number of carbons on this end of the acid chloride. You can change the number of carbons on this end. There we go. The trick though is that you have talking too fast, mouth can't catch up. Friedel-Crafts alkylation reactions require alkyl groups attached to the halide. So you always use an alkyl halide if you're doing Friedel-Crafts alkylation. That makes sense. And what we'll see in the next video is you can't use this molecule because that's not an alkyl group, right? That's got an alkene in it. Alkyl groups contain alkanes, single bonds between carbons. So no, this one won't work. And the triple bond with a halide won't work either. However, the alkyl group doesn't have to be methyl. It could be primary, could be secondary, it can even be tertiary. So lots of variety, which makes it really useful because it gives scientists a lot of choices. The halide, chlorine, bromine, iodide, not fluorine, which we already mentioned. The second reaction, Friedel-Crafts acylation, that's always going to use an acid chloride, and we're not going to vary the halide. They're always going to use an acid chloride, at least I will. And the acid chloride can contain any number of carbons in any form. Yeah, primary, secondary, tertiary, whatever, branching, rings, whatever. Yeah, actually we did one where the benzene ring had an acid chloride. And that works, right? Oh, and there can be other things on here too. Whatever, tert-butyl group. And you start with the benzene ring, and you get to put this whole group on here. Where does it go? Wherever the halide is. So copy this whole reagent. Get myself a little more room because I created a crazy looking reagent. So let's just copy the reagent. We got the tert-butyl group down here. I put this up here looking like that. And then we have, whoa, I missed. Hey, too much. There we go. Okay, here's my acid chloride. And right where I'm about to draw in the chlorine, that's my point of connection on the benzene. We're going to remove a hydrogen. That's nice about skeletal drawings. We don't have to draw in all 6 H's, but they're there. I'm going to choose to pick the hydrogen attached to this carbon to be substituted out, and there's your product. Yep, Friedel-Crafts reactions are the most useful because of this cool feature, at least from a scientist's point of view. This is cool. You can decorate your acid chloride however you want. We'll talk about some limitations in the future. It can't be just anything. More on that later. But there's quite a variety you can use. Oh, yes. So I promised to talk a little bit more about the fluorinating agent, the one that creates F+. And you can imagine that's extremely difficult to do. Fluorine is the most electronegative atom. What are you doing being positive? It does not like being positive. So it's very difficult to create. This reagent can do it, however. So what do we got? We got 2 amines, 2 nitrogens. The nitrogens have ethyl groups connected to them. How many ethyls in this whole molecule? 3 of them. And then the diamine, there's also a methyl group with a chlorine. That's weird. It works. Trial and error, I guess these scientists discovered this is a useful reagent. Nitrogen's bonding 4 times, giving it a positive charge. Nitrogen prefers 3 bonds, but it can make 4, just like in the ammonium ion. Nitrogen's making 4 bonds. Anyways, because the nitrogens are both positive, you need some counterions. And these counterions can't interfere with the reaction. But boron tetrafluoride, what's the other word? Tetrafluoroborate. It's the other word for these anions. So now it's a neutral molecule. And the fluorine's connected to this nitrogen. And I believe the key here is that nitrogen wants its lone pair back. Nitrogen prefers 3 bonds, 1 lone pair. So this fluorine, occasionally, and it's kind of crazy. You'd think fluorine more electronegative would steal these electrons. but sometimes nitrogen gets to take those electrons. Okay, I've overanalyzed this reagent. The whole purpose, the only thing you need to know is if I draw this crazy looking molecule over the reaction arrow, right? I say, hey, predict this product. And I draw in, let's see, let's draw it a different way. I might just stop there. So if I just drew that, you go, Dennis, what the heck is that? I can barely draw this. See these squiggle marks. Oh, wait, is that an ethyl group, an ethyl, an ethyl? Oh, wait, there's a fluorine here. This is F, whoops, that's supposed to be a T. Theta BF4. And what does that do? It puts a fluorine on the ring. Wherever there was a hydrogen, there's 6 of them here, so you pick one. Let's be different. Let's pick the bottom one. Whatever. Substitute the hydrogen here with the fluorine. Cool. So that you just need to be able to recognize this. So if I draw it, you can identify it. You don't have to draw this on your exam. If I say, hey, give me the reagent that puts fluorine in a ring, then you can choose to draw this. Most students won't. They'll probably just draw in this acronym or abbreviation. Cool. And several years ago, another student had an excellent idea. Said, that's so hard to remember. I need a little saying, a little memory mnemonic. Help me remember it. And this is what she came up with. So I share it with you. F Theta BF4 might stand for fluorine takes electrons dancing and brings 4 friends. So the theta is takes electrons dancing and then brings 4, well, they swap there, bring 4 friends. That's cool. So yay, nice little shortcut. What's all this gibberish in here? Thankfully, all 8 types of EAS, electrophilic aromatic substitution reactions, follow the same mechanism. Oh my goodness, thank you. Right, so we just saw 8 reactions. Do we get 8 different mechanisms? No, we got 1 mechanism. All you have to do is change a reagent. So if you're putting fluorine on the ring, and I think the mechanisms talks about how to put bromine on the ring, well then just copy the whole mechanism, and every time there's a BR, change it to F. Do you want to know how to do the nitration mechanism? Look at the mechanism from bromine, change BR to NO2, and you got it. It's exactly the same. It's not always the case in organic chemistry, but it works here. How about for Friedel-Crafts? Look at the mechanism for bromination, and every time there's a bromine in your mechanism, change it to the ethyl group, and you got the mechanism for Friedel-Crafts alkylation using ethyl chloride. Sweet. Because that mechanism is so powerful and so important, I can just put it into a separate video. So take a look at that. I got the link to it here, but it's also in the assignment folder. That's not what it's called. It's also in the assignment for electrophilic aromatic substitution reactions on Canvas. You can just click on the link within Canvas. Cool. Okay. So the rest of, key concepts, I didn't cut and paste it here in this document. The rest of key concepts reviews the mechanism, but take a look at the video. I think that's much more helpful. Well, let's finish up this video with a quick little summary of the 8 reactions that we've seen. I'll just draw them a little differently. Some of you might recall last semester had these reaction flow charts or reaction, what do we call them? Explosion charts. Because it looks like you start with a molecule and kaboom, you blow it up into a bunch of different molecules. So let's draw one here. This is another way you can memorize your reactions. You don't have to do it. It's just another idea. Anyways, you start with benzene, and what can you do to it? Well, 8 different things. Maybe you want to put fluorine on a ring. So fluorine takes electrons dancing and brings 4 friends. And then you decide, where do you want to put that fluorine on? I'm going to put it over here to be different. Okay, I like fluorine today, but tomorrow I want to put on chlorine. How you put on chlorine? Start with Cl2, add the iron form with 3 chlorines, and that'll allow you to put chlorine in a ring. And over here this time. Any one of these 6 can come off. 6 hydrogens on the benzene ring, you choose which one. How about bromine? Same pattern as chlorine. Br2, FeCl3, and then somewhere on benzene, top this time, goes hydrogen swaps out with the bromine. Iodide, similar pattern. It's I2 followed by not iron, it's copper. And there's only 2 chlorines. I know, that's annoying. Iodine, you go over here. Cool. So there's 4 of the 8 reactions of the electrophilic aromatic substitution reactions that put a halide on the ring. But you can also put on a nitro group. Let's draw the nitro group first. And I'll put it up on top. Nitro is NO2, but the reagent is HNO3. But you also need sulfuric acid as a catalyst, H2SO4. All these numbers and suffixes you have to remember. What are they called? Subscripts. You can also put the sulfonic acid group on there. Where do you want to put it? Okay, I'll be weird and draw it backwards, because that might be how it might appear on the exam. You know, we'll get used to that. Okay, I do get a little weird with my drawing sometimes. There are days when I like seeing NO2 drawn NO2. And there's other days where I'm like, which atom is attaching to the ring? The nitrogen is in nitro. So then I'll draw benzene, put the N there, and then I don't want to put O2 on the right because it looks like the oxygens are attached to the ring, but they don't, right? The nitro group has a nitrogen attached to the benzene ring, and then one oxygen is double bonded, the other one is single bonded. Nitrogen's making 4 bonds, oxygen only 1. So they have, they're not bonding normally, like honk would tell you. Remember that acronym, 1, 2, 3, 4, HONC? That's the number of bonds they prefer to make. Nitrogen prefers 3 bonds. If it makes 4, it can't be neutral. It's positive in this case. Oxygen prefers 2 bonds. Hey, there's only 1 bond to this oxygen. Well, it's not neutral then. In this case, it's negative. How do you put the sulfonic acid group on the ring? Well, you need the, let's try it this way. There we go. So the SO3H group needs SO3 and a source of H, H2SO4. That's kind of how it's stuck in my head. All right, now there's 2 ways of putting, I don't know if I gave myself enough room. Let's make bigger arrows. There's 2 ways of putting carbon on the benzene ring. Start with the benzene ring, and then do you want an alkyl group? What kind of alkyl group do I want today? How about, I don't know, how about we put on cyclopentane? So I connect cyclopentane. I mean, how do you do that? Well, you have to start with cyclopentane. And wherever the point of connection is, that used to have a halide. And then use aluminum chloride. So you have to use chlorine here in your catalyst. And that's actually a nice visual clue. If you see AlCl3 anywhere, it's Friedel-Crafts. This is the only reaction in organic chemistry where we use AlCl3, at least in my class. Okay, however, the halide doesn't have to match chlorine. It can be anything. And my favorite halide is bromine, so I probably end up putting a bromine there. But there you go. To put alkyl groups, alkanes, onto your benzene ring, have the alkane attached to a halide, and use aluminum chloride. If you want a ketone, so I want a ketone, and hey, how about the cyclopentane ring on this side? Not a double bond, single bond. What fit here? There we go. There's my cyclopentane ring, part of the ketone, and where the ketone stops, that's where the acid chloride begins. And again, use aluminum chloride for this Friedel-Crafts acylation reaction. There we go. It's kind of messy, but there's all 8 reactions drawn in an explosion chart for you. All right, I'll see you in the next video.